In this video, I'd like to talk about the topic of implicit differentiation. Now, before we get into the differentiation portion of this, let's talk about this word implicit. And what does implicit mean? So, up until this point, we've been taking derivatives of functions, where y is a function of x, But in the grand scheme of things, mathematically, we have, well, let's say this is the set of all functions out there. And that set of all possible functions is contained within a larger set of things called relations. Now, some relations are functions. So, like, for example, basically, let's say some relations are functions, but some relations are not functions. But every function is a relation. So what I mean by that is, let's say you have x squared plus y equals 1. Well, that is a relation that is also a function. And it's a function because we can solve for y. We could express y as a function of x. So we have one independent variable, x, and one dependent variable, y. So we could say y equals 1 minus x squared. Okay? Now, when you take an equation or relation and isolate y or solve for y or put it in function form, this is called explicit form. And up until this point, all the derivatives that we've been taking have been applying derivative rules of equations in explicit form or relations that are functions. When you have the sort of the x and the y mixed up together and neither one variable is isolated, we call that implicit form. Now, in this case, it was very easy to go from implicit to explicit. Solve for y was one step. We just subtract x squared from both sides. And it's not always that simple. And also, it's not always possible. So if your function, or if your relation is in here, if it's a function, then you should be able to solve for y. But if your relation is not a function, that means y is not defined as a function of x. Well, then it's not necessarily possible, not possible at all to convert from implicit form to explicit form. So let's look at a very basic non-functional relation. Let's just change that y to a y squared. So now we have a circle. So in implicit form, we have x squared plus y squared is equal to 1. Now, this is not a function, and we cannot solve for y here. We cannot isolate y in one single expression. We can, but we would have to sort of define it piecewise. And we could say y is equal to, well, it's going to be the square roots of 1 minus x squared for y values greater than 0. And it's going to be, actually we could be more specific and say for y values that looks like a 4. For y values between 0 and 1 and negative 1 minus x squared for y values from negative 1 up to 0. All right, so obviously in this case, the implicit form is much simpler. But it's still a case where we could break it up into, so basically what we're doing is we're taking a non-functional relation and breaking it up piecewise, where each piece of the relation is a function. It's basically the top half of the circle, or the top semicircle, and the bottom semicircle. All right, so now I want to focus on the left-hand side, taking the derivative implicitly. So let's look at the derivative operator. So this means the derivative with respect to x of something. So there's got to be something in the brackets. So one thing we've seen is that the derivative of x is equal to 1. And the derivative of y is equal to, well, we have multiple notations. We could say y prime or dy over dx. So basically, the two d's and the x, that's one. That's basically one symbol. The d dx is one symbol, and that's being applied to the y. So shorthand notation for this is dy over dx. Okay, and so that's basically it. We have the same rules that we've been applying, the power of product, quotient, and chain rules. We have rules for trig functions, the sum and difference rule, the constant multiple rule, all of those. So we're going to apply those in conjunction with this one here, the fact that the derivative with respect to x of the variable y is dy over dx. All right, so let's look at an example. Let's say y cubed plus y squared minus 5y minus x squared equals -4. Yeah. If we want to look at the graph of this, we'll easily and quickly see that it's not a function. The graph looks sort of like a infinite urn or a vase, maybe something like, that's probably going to be more pronounced, something like this. And so that's definitely not a function, but it's the graph. It's the graph of this equation. And so that graph is made up of points. And then anywhere on that graph, we could talk about the line tangent to the graph. And the slope of that line is the derivative, dy over dx, evaluated at that point. All right, so we should be able to apply the same processes before. The derivative gives the slope of the tangent line. So solve for dy dx. Find dy over dx. Okay, so we have some guidelines for implicit differentiation. Actually, let me move this up here. So we'll differentiate both sides of the equation with respect to x. So we have y cubed plus y squared minus 5y minus x squared equals a -4. So we'll do the derivative of the left is equal to the derivative of the right. Okay, so once we take the derivative, then there's going to be some dy dx's in there. And so we're basically applying the chain rule. So when we take the derivative of, so let's look at this first term here, the y to the third power. So if we take the derivative of y to the third power, what does that look like if we apply the chain rule? Well, I'm going to throw in some parentheses there that you normally wouldn't include because they don't really serve a purpose, but in this case it's more of a visual aid. If we do this, then you'll see we have an outer function, which is the third power, and we have an inner function, which is the y. So the chain rule says you take the derivative of the outer function. That's the power rule. 3 comes down and drops by 1. So that's the derivative of the outside function, while the inside function stays the same, times the derivative of the inside function, and the derivative of y we just discussed is dy over dx. So the derivative of x cubed is just simply 3x squared, but the derivative of y cubed is 3y squared times dy over dx. All right, so we'll apply the derivative term by term. So the derivative of y cubed we just saw is 3y squared times dy over dx. Applying the chain rule again to the y squared, so that's 2y to the first power times dy over dx minus 5 times the derivative of y, which is again dy over dx, minus 2x to the first power is equal to the derivative of -4, and the derivative of a constant is 0. Okay, so we've taken the derivative of both sides of the equation with respect to x. Now, step 2, so now we're trying to solve for this dy dx, right? So let's move everything with a dy dx on one side and everything without it to the other. In the guidelines it says the dy dx's all go on the left side. It doesn't have to be the left side. If they start off on the right, just leave them on the right. Just one side gets all the dy dx's, the other side gets all the terms that don't have the dy dx. In this case, it's just the minus 2x. So we can add 2x to both sides to bring that over. And we'll have 3y squared dy over dx plus 2y dy over dx minus 5 dy over dx. Okay, put all the dy dx's together and then factor them out. So if we factor out the dy over dx, let me use soft parenthesis, we're left with a 3y squared plus a 2y minus a 5. And finally solve for dy dx, which in this case means one step, divide both sides by that quadratic expression. So we have dy over dx is equal to 2x over 3y squared plus 2y minus 5. And there is our derivative, or our expression that gives us this slope of a tangent line. All right, maybe we'll do one more example. That's reserved only for answers. So let's say, for example, find dy over dx for the sine of xy equals x. Sine of xy equals x. Okay, so take the derivative of both sides. we'll take the derivative of both sides of the equation, sine of xy and x. Now, on the left-hand side, it looks like we have a chain rule situation because we have the sine function on the outside and we have the xy on the inside. And we also have a product here. So we're going to have to, while we're applying the chain rule, we're going to have to apply also the product rule. So, starting on the left-hand side, the derivative of the sine function is the cosine function. So we take the derivative of the outer function. Inner function remains the same, times the derivative of the inner function, which is the product x times y. And on the right-hand side, the derivative of x with respect to x is 1. Okay, so now applying the product rule. So we have cosine of xy times, so the product rule says we take the derivative of the first times the second. So the derivative of x is 1, so 1 times y, plus the first times the derivative of the second, and the derivative of y is dy over dx. So we're using chain rule. Here we're using product rule as part of the chain rule here. Okay, so now we've got to solve for the dy over dx. So let's subtract, or actually this is multiplication. So let's divide both sides by cosine of xy. And the 1 over the cosine function is the secant function, so we could get rid of that fraction by just writing secant of xy. We can subtract y from both sides to get rid of this y on the left. So we've got secant of xy minus y. And finally, divide both sides by x, so we'll have dy over dx is equal to the secant of xy minus y, all divided by x. Okay, and so that does it for that example. Now, the last thing I want to say about implicit differentiation is this. If we go back and we look at our guidelines, step 1, differentiate both sides of the equation with respect to x. Well, you could differentiate with respect to anything. And so one thing we're going to see later, actually in the next video, is using this idea of implicit differentiation to solve word problems that involve rates of change. And to do that, we're going to take derivatives not with respect to x, but with respect to time. Because we're going to be looking at how physical quantities change over time. Remember, calculus is the mathematics of change, and the derivative tells us the instantaneous rate of change. And we will be talking about things changing over time. All right, so going back to the derivative of we said, well, the derivative of x with respect to x is equal to 1, but the derivative of y with respect to x is not 1. It is dy over dx. Okay, that we've seen. So if we say, for example, the derivative of, for example, the derivative of x to the 4th power versus y to the 4th power. Well, the derivative of x to the 4th, we use the power rule, which says the 4 comes out front, drops by 1. Y to the 4th, we're applying the chain rule. We can actually think about both of these in the context of the chain rule. So the derivative of x to the 4th and the derivative of y to the 4th. Well, the power rule says the 4 comes out front. Let me leave that off for now. The 4 comes out front, drops by 1. So the derivative of the outside function, while the inside function stays the same, which is the y, times the derivative of the inside function, which is dy over dx. So if we apply that same logic here on the left, the 4 comes out front, drops by 1. Inside function stays the same. And then we multiply by the derivative of the inside function. And the derivative of x is 1, which is why we don't need that times 1 there. But technically, it's there as a result of the chain rule. All right. So, last thing to do is take the derivative with respect to, take the derivative with respect to time. So now we're taking the derivative with respect to time. So the derivative of x is no longer 1. The derivative of x is dx over dt. And the derivative of y would be dy over dt. All right, and so it's important to distinguish between the operator, which I have in red, and the variable. And so what we're going to be doing is taking derivatives, since we're going to be looking at how actually like physical quantities change, the rates of change of physical quantities with respect to each other. We call these related rates. And so we're going to be taking derivatives of, in many cases, not every single one, but in many, many cases, we're going to be taking derivatives with respect to time of geometric formulas. So, for example, applying implicit differentiation to, let's say, take the derivative of the formula for volume of a sphere. 4/3 pi r cubed. All right, so you could think about blowing up a balloon or something like that. You know, as you increase the volume of air, the balloon gets bigger, so the radius goes up. So volume and radius are related to each other by this equation. Oop, that should be a t. I think I said t, but wrote x. We're taking the derivative with respect to time. You could take the derivative with respect to time of, the good old Pythagorean theorem. X squared plus y squared equals, say, c squared for the hypotenuse. All right, so we could apply the idea of implicit differentiation to these formulas. So on the left, the formula for volume, well, if we take the derivative of the left, the derivative of v with respect to t would be dv Oh, sorry about that. We had a slight technical blip. So the derivative with respect to t of v is dv over dt, and that's equal to, well, 4/3 is a constant, pi is a constant, and now the derivative of r cubed, just like up here the derivative of y to the 4th, the derivative of r cubed is 3 times r squared times dr over dt. And then if we needed to, we could do something with this. The 3's cancel, and depending on the problem, we may want to solve for dr dt or leave it in this form. Pythagorean identity. The Pythagorean theorem, the derivative of x squared would be 2x times dx over dt. The derivative of y squared would be 2y times dy over dt. And let's say c is a constant in this case. Derivative of constant is 0. So this is what we're going to take and apply at the next level when we're looking at word problems that use these rates of change, the derivative with respect to, well, I mean, basically, you could take the derivative with respect to anything, and if this thing right here is the same as this thing right here, you get 1. So d over dx, the derivative with respect to x of x is 1, or the derivative with respect to t of t is 1. If they're the same, you get 1. If you have the derivative with respect to something here of, I don't know, something else, we'll say a triangle, you get d of that over d of that. I guess it's a sort of loosely informal way of distinguishing the difference. All right, so that about does it for this. Next video will be on related rates.